In 7.4, we're going to study 3 properties of logarithms. And I should almost give extra credit to anyone that has any clue what I'm talking about here. This reference, this joke. Yeah, okay. So continuing on. Recall the properties of exponents. First, the product property said, if I am multiplying terms with the same base, well, there are 4x's here, there's 7x's here, I just would add 4 plus 7 to get x to the 11th. So if I'm multiplying terms with the same base, I add the exponents. If I'm dividing, 4x's in the denominator would cancel with 4x's in the numerator. So I would actually just subtract the exponents, and I would be left with x to the 3rd power. If I have a power to a power, 2 exponents, x to the 4th times itself 7 times, well, that would give you x to the 4 times 7, or x to the 28th power. So if I have 2 exponents, I just multiply them together. Now wait a minute, what is a logarithm? Well, a logarithm is an exponent. So these 3 properties are also properties of logs. So let's explore the first one. First, we have the product property of logarithms. So what this property is saying is if I'm adding logarithms that have the same base, so something like this here, I've just thrown in some numbers, then that would be the same as if I multiplied the arguments together, 4 times 8, and said log base 2, so same base of 32. Why does this work? Well, think about what is a logarithm, an exponent. When do I add exponents? Well, if we go back here, I would add exponents if I was originally multiplying terms with the same base. So I can combine these into one logarithm by multiplying the arguments together. And let's just check this out. 2 to what power is 32? Well, that would be 5. 2 to what power is 4? That would be 2. 2 to what power is 8? 3. Does 5 equal 2 plus 3? Sure. Now, instead of using a numerical example, we could also look at the proof. So here's the proof. If I start with this and I call that x, and I'm going to call this y, I could rewrite these in exponential form. So b to the x is m, b to the y is n. Then if I multiply m times n, that would be the same as multiplying b to the x times b to the y. So now I'm here. And here's where that exponent property comes into play. If I'm multiplying terms with the same base, I add the exponent. I could rewrite this as a log. My base is b, my exponent's x plus y. That should give me out my argument. And then the last thing I'm going to do is, well, what was x? If I go back to the original, x was log base b of m. Y was log base b of n. And this is really the proof for why this property works. Now, I won't ask you to prove the log properties, but if you're curious, this is what's happening. You need to know how to use the log properties, not necessarily prove them. But the big thing is, see here how they tie back to what we studied about exponents. So if I'm originally adding the logarithms, and a logarithm is an exponent, I would add exponents if I was originally multiplying terms with the same base, just like we talked about here. Second log property is the quotient property of logarithms. So if I'm subtracting logs with the same base, well, a log is an exponent. When would I subtract exponents? That would occur if I was originally dividing terms with the same base. So I could combine this log into one if I divide the arguments. So here's just a numerical example. If I have, notice I have the same base. If I'm subtracting the exponents, if I'm subtracting the logs, I could combine this into one log by taking the first argument divided by the second, or 125 divided by 5. So from here I have log base 5 of 5 should equal log base 5 of the rest of the stuff. There we go, that looks a little better, sorry. 125 divided by 5 is 25. So now I'm to this line. 5 to what power is 25? Well, that would be 2. 5 to what power is 125? That would be 3. 5 to what power is 5? That would be 1. So, yep, this equation actually works. Now, if I look at the actual proof where I'm not just plugging in numbers, here it is. Notice in this proof, if you want to pause the video and take a further look at it, you could. It starts very similar to the proof of the product property, but now I'm setting up a quotient. If I'm dividing terms with the same base, I end up subtracting exponents, and then in the end, I go back and substitute those original values in. So these are the exponents that I was subtracting back up here, since a log is an exponent. I combine them by dividing those terms. Third one, the power property of logarithms. Essentially what this property is saying is if I have an exponent in my argument, I could bring that exponent out front and it should be equivalent to the original expression. So numerically, it's saying, all right, if I brought this exponent on the argument out front in front of the log, I'd have something like this. 5 times log base 2 of 8. These should actually be equivalent. So let's take a look and simplify. This would be log base 2 of, well, 8 is like 2 cubed, right? So I have like 2 cubed to the 5th power. Or this would be log base 2 of 2 to the 15th. So this is saying 2 to what power is 2 to the 15th? Well, this would equal 15. Over here, if I bring the 5 out front, I'd have 5 times log base 2 of 8. Well, 2 to the 3rd power is 8. And I end up kind of doing the same thing where back here, I multiplied 3 times 5. That's your power property. An exponent to an exponent, you'd multiply them. Same thing ends up happening here. This is the exponent on 2 that would give me 8. I'm still multiplying that by 5, and I should end up getting out the same answer. So here's your tie-in to the exponent properties we learned, such as this. Just multiply those terms together. So here is the proof. Feel free to take a closer look at it. If you are examining this proof at this point, you're multiplying each side by n to continue on, and then I end with that product, or that power property, of logarithms. Now here's the big punch of this lesson. Why do I even care? Well, first off, these properties allow me to combine 2 logarithms into one, and it might allow me to evaluate expressions that I couldn't before. So right now I'd be thinking like, well, 6 to what power is 2? Well, I don't really know that. 6 to what power is 108? I might not know that off the top of my head. But if I combine these, well, a logarithm is an exponent. So when do I add exponents? Well, that happens if I'm originally multiplying terms with the same base. So I could combine this into one logarithm by multiplying the arguments. So my base is 6 on each of these. So log base 6 of, I could combine this into one log by multiplying the arguments together. Or log base 6 of 216. Now what does this mean? Well, this means 6 to what power is 216? Well, 6 to the 3rd power is 216. So by combining these into one logarithmic expression, I can actually end up evaluating these, the sum of these logs. Let's look at the quotient property in action here. I am subtracting these logarithms, and logarithms are exponents. So I would subtract the exponents if I were originally dividing terms with the same base. So I can combine this logarithm into one logarithmic expression if I divide the arguments. It always has to be the first argument divided by the second argument. Now 3 over 48 is the same as 1/16. So back in the original, 4 to what power is 3? Well, I don't know that. That would be a decimal. But if I combine these, I actually end up getting something that I can evaluate. 4 to what power is 1 over 16? Well, 4 squared is 16. So 4 to the negative 2 power would give me 1 over 16. And that should be equivalent to log base 4 of 3 minus log base 4 of 48. Now I want to show you a couple different ways to do this example. You could use the power property. So if I see a number out front, I can bring that up to the exponent in the log. So if I'm multiplying that 2 out front, I can rewrite this as log base 6 of the quantity 6 squared of 6 squared. And then if I take 6 squared of 6 squared, well, 6 squared of 6 times itself, 6 times 6 is 36, square root of 6 times square root of 6 is 6. That should actually equal 216. So I actually have log base 6 of 216. 6 to what power is 216? That would be 3. Now another way you could do this is I could just keep the 2 out front, and then I could separate the argument into 2 logs that I'm adding together, which goes back to the product property. If I'm adding logs, that's the same as multiplying them together. So now I'm just kind of breaking that log up into 2 different logs. And 6 to what power 6? Well, that would be 1. 6 to what power is the square root of 6? That would be a half. And 2 times 1 1/2 would give me the same answer. So just to show that there are alternate approaches to solve this problem. Last few examples, let's look at solving some equations involving multiple properties of logarithms. So first off, on this, if I wanted to, I could combine that left side into 1 log. So a log is an exponent. If I'm subtracting exponents, that would originally happen if I were dividing terms with the same base. So I could rewrite this as log base 5 of that first argument divided by the second argument. And then on the right side, I actually have that power property where I can bring this 2 up and throw that on the exponent of the argument. So this is the same as log base 5 of h squared. 625 divided by 25, that would actually be 25. So if I divide this out, I get 25. On the right side, I still have log base 5 of h squared. I know there's a couple places I could go from here, but if these logs are equivalent and they have the same base, wouldn't my arguments have to equal each other? So 25 would have to equal h squared. And if I take the square root of each side, you should find, well, h should equal 5 or negative 5. But careful, if I check back into my original equation, the argument can't be negative. There's no exponent I could throw on 5. So 5 raised to any power is never going to give me out a negative number. So the negative answer doesn't make sense. H would have to equal 5. Now why don't you pause the video and give this problem a try? You'll actually use all 3 log properties that we discussed here. So your goal should kind of be, can you combine all of these 3 logs into 1 eventually and solve? So pause the video and give it a try. So first thing I looked to do was I just brought that 3 up as the exponent on 2. Note that these are common logs, so the base on all of these is 10 if nothing's written. If I want to keep combining, well, log is an exponent, so when do I add exponents? If I was originally multiplying terms with the same base. So I could combine those first two logs by multiplying. 2 cubed is 8, so I really have 8 times 5. And let me write it out. I'll write out another line. So I'm here. So combining these logs, multiply 8 times 5, which gives me 40. Now I could keep combining. Please do not say this is log of 30. Totally illegal. If I am subtracting exponents, that occurs if I was originally dividing terms with the same base. So I could combine these into one by dividing the arguments. So at this point, I have log base 10 of 4 equals log base 10 of p. Therefore, since these logs equal each other, they have the same base. P has to equal 4. Now note that on some of these, there may be multiple approaches to solving them. Like actually on the previous one, could I say, well, 5 to the 4th is 625, 5 squared is 25, and say immediately, well, this side is 4 minus 2, or 2, and then solve the equation from here? Sure, so maybe you thought of different approaches, but we should end up with the same answer. Now I just want to end with a word of caution. Make sure you know how to use these log properties. If I were to solve an equation like this, I could bring that exponent, or that x up to the exponent on your argument, and do something like this. So then, if these are the same base and these are equivalent, well, then the arguments have to be equivalent. So 2 to what power is 16? Your answer should actually be 4. You could test it out on your calculator. If I take 4 times the log of 2, that should equal the log of 16. I often see people do things like this. They divide each side by the log of 2, and then they'll cancel. Well, this isn't one of the properties. If we look back to the original page, the product property, quotient property, and power property, and nowhere am I talking about when do I divide exponents. And I'll see people that want to say, oh, well, this is the log of 8. No, totally illegal. This is saying 10 to what power is 16, 10 to what power is 2. If I divide those exponents out, I'm not getting 8. So just careful. This would be the appropriate way to solve that problem.